Okay, hi everyone. Last video we were introduced to vector spaces, and the key things you should bring from vector spaces from that lecture is that a vector space is a collection of things, which we call vectors, and two operations. One is what we do when we add two vectors together, and the other one is when we multiply vectors by scalars. And when you do either of those things, you need to get another vector in the vector space. You can't leave it, you got to stay within it. So those are the two things we do. And then we also talked about subspaces, and a subspace is basically a subset of a vector space. It's not necessarily all of them, but it's some of them. And then that subset is also a vector space. So it satisfies all those 10 properties that a vector space satisfies. Okay, so I'm going to use one example throughout most of my lecture today to kind of illustrate things. And so the ones I'm going to talk about are going to be matrices, which are 2 by 3 matrices. And you write them like this. I'm trying to remember how I write them, like this. So these are 2 by 3 matrices, which means they're things that have 2 rows and 3 columns. So I'll just call it A, B, C, D, E, F, just to be simple. Okay, it's things that look like that, where those are numbers. Okay, and so that's going to be the vector space that we use to illustrate lots of things. Okay, so the first thing I want to define for you is the idea of a linear combination. And I'm following the textbook here. A linear combination is what you get by just doing what you can do with vectors. What can you do with them? You can multiply them by scalars, and you can add them together. So for example, if you have a couple vectors, and I'm always going to use x's as vectors, and I'm going to use a's or letters towards the beginning of the alphabet, A, B, C's, for scalars. So for example, if you have a vector space with vectors x1, x2, and x3, and if you take those and multiply them each by a constant, a1 plus a2 x2 plus a3 x3, that's a linear combination of vectors. As I say, you do everything you can. That's all you can do with vectors. You can multiply them by scalars, and you can add them together. So that's called a linear combination. Okay? So that's the first thing you need to understand from section 5.2. Then, so over here, a linear combination might be something like 5 times the vector 1, 0, 0, 0, 0, 0 plus 3 times the vector 1, 2, 5, 1, 3, 2 plus 6 times the vector 0, 0, 1, 0, 1, 5. Okay, that would be a linear combination of vectors in there. Okay? Very good. Okay, now, if you have a couple vectors, like let's take a couple vectors in here, and I'll take some kind of simple ones. There's a vector. And there's a vector. Two very simple vectors. So first of all, if I took all the linear combinations of these vectors, of these two vectors, what would I get? All possible linear combinations. That is, I take some constant A times this one, plus some constant B, some scalar B, I should say, times this one. What am I going to get? Do you agree that I'm going to get all the 2 by 3 matrices that have an A in the first spot and a B in the second spot and zeros elsewhere. Agree? It's going to be all the things that look like this. So this could be anything, this could be anything, and zeros everywhere else. Okay? So that's called the span. The span of a set of vectors is the collection of all linear combinations of them. Of all linear combinations of that set. Okay? So as I say, for these two vectors right here, the span would be all the things that look like this. Okay? That would be the span. Okay? Now, what I want you to notice is that this span is a subspace of my original vector space. See that? It's a subspace of it. What does it need to do to be a subspace? It has to satisfy all 10 of those properties, but most of those properties we know are fulfilled because this being a vector space, already we know it's fulfilled. So we know that you can add them in either order and associative property, all that stuff works. Remember that the two things we need to check in order to be a subspace is that we need to check that if you add two of these things together, you're going to get something else. So let's check it out. If I have something that looks like this, let's call it A1, B1, 0, 0, 0, 0, and I have something else in there, let's call it A2, B2, 0, 0, 0, 0. There I am, I'm adding two of those things together. Do you agree that I'm going to get what? I'm going to get A1 plus A2, and then B1 plus B2, and then 0, 0, 0, 0. So sure enough, I get something else that looks like this. So it's something else in my subspace. So that is checked. And then the other thing we have to check is that if I take this thing and multiply it by a scalar, I'm going to get back in there again. Those are the two things we need to check. And sure enough, if I take that thing and I say multiply it by alpha, what am I going to get? I'm going to get alpha A, alpha B, 0, 0, 0, 0. So sure enough, you have something else that looks like that. So that's true. That's true in general, that if you have the span of a set of vectors, if you take the entire span of a set of vectors, that's going to be a subspace of the vector space that those vectors came from. Okay? So that's theorem 524, that given, I'm not going to write down everything precisely the way I have it in the textbook. Theorem 524, basically given a set S, which is a subset of your vector space, then if you take the span of all those elements in S, that is a subspace. A subspace of V. Okay? My computer just shut off there. Okay? So you start off with, for example, any subset you want, and you take all the possible combinations of those. You multiply them by all the scalars, and you add them together, and you're going to get yourself a subspace. So these two right here, if you take all linear combinations, you're going to get a collection of things like that. And notice that that's a subspace, because as I say, you add two of them together, you're still in there, and you multiply it by a constant, you're still in there. So that's the idea of a span. Okay, let's do another example, geometric example, just to show you how this works too. If you're dealing with let's just take the plane. Okay, take the plane and take one vector in the plane. Okay, there's a particular vector. So what's the span of that vector? There's just one vector there, so you can't add it to any other vector. That's the only one there. So you just multiply it by all possible constants, and you agree? If you multiply it by 2, you'll be out here. If you multiply it by 3, you'll be here. If you multiply it by -1, you'll be there. If you multiply it by a half, you'll be there. And you're going to end up with all the vectors along that line. And so all the vectors along that line is a subspace of R2. Okay, so there's an example. If you start off with R3, so here's the x-axis, the y-axis, and the z-axis, and you take one vector and another vector, and you take all linear combinations of those two vectors. So you add them together. If you add them together, you're going to be right there. If you multiply this one by 2 and then add this one, multiply it by 2 and then add this one, you're going to be right there. So you take all possible combinations of those vectors, you're going to end up with a plane that goes through the origin. Okay, that's going to be a plane that goes through the origin. So again, you start off with any set and you take the span of all those vectors, and you're going to get a subspace. Suppose let's do another example. Suppose that our vector space is all polynomials. Okay, all polynomials. What do I mean by all polynomials? I assume you know that. Polynomials. Okay, and so it's everything that's just powers of x with constants in front, and you multiply them together. And let's just take a particular subset. So let's let S be the subset. I'll take some easy ones again. I'll take x, x squared, and x to the 5th. Okay? There's 3 particular polynomials, okay? And so now you take the span of all those. So what's the span of all of them? The span of all of them are going to be all vectors of the form ax plus b times x squared plus c times x to the 5th. Anything of that form is going to be in the span of this set. And notice if I take 2 of those things and add them together, I'm going to get something else like this. If I multiply this thing by a constant, I'm going to get something else like that. If I multiply it by 0, or by 0, I'll get the 0 vector. And so that's in the subspace as well. So there's the subset, and if you take the span of all those things, you're going to get a subspace. Okay? So, that's all important. Then, another key idea, other than span, is the idea of linear independence. Okay? What do we mean by linear independence? Basically, in real life, 2 things are independent if they have nothing to do with each other, right? The rain today in Florida and the weather on Mars. Okay, those 2 things are independent. Probability uses that word too if they have nothing to do with each other. And the same thing holds here. These 2 vectors here, there's no way I can affect this vector with this vector. I can't get there from this one. They are independent of each other. So these 2 vectors are linearly independent. On the other hand, if I were to take this vector and this vector, they are linearly dependent, because by starting with one of them, I can get to the other one, right? If I start with this one and multiply it by 5, I can get there. If I start off with these 2 vectors and throw in a third vector, 3, 5, 0, 0, 0, 0, these 3 vectors are linearly dependent again, because by multiplying this one by 3 and multiplying this one by 5 and adding those 2 together, I'll get this one. So these 3 are linearly dependent. On the other hand, if I had a 2 right here, then these three vectors would be linearly independent, because there's no way I can get this one from a combination of those. Okay? So let me write down the definition. Here's a definition. The set of vectors x1, x2, let's go out to x to the n, is linearly independent if, here's the precise way to say it. Let me explain it first, and then I'll tie this all together. They're linearly independent if the only way that a linear combination of those things can be zero, the zero vector, the only way that those things can add up to the zero vector is if each one of those constants is zero. Okay? The only way, so for example, if I had a times 1, 0, 0, 0, 0, 0 plus b times 0, 1, 0, 0, 0, 0, if that were equal to the zero vector, here's the zero vector in 2 by 3 matrices, do you agree that the only way that this combination can be equal to this is if A is equal to 0 and if B is equal to 0. Do you agree? On the other hand, well, let's go back to this example I had again. If I have 1, 0, 0, 0, 0, 0, and then 0, 1, 0, 0, 0, 0, and if I had 5, 3, 0, 0, 0, 0, running out of room here. How can those things add up to the zero vector? These, remember I said, are linearly dependent. I can get this one from these two, which means that basically how can I get the zero vector here? I can multiply this one by -5, and then multiply this one by -3, and then just add it to that one, and then by adding this combination together, I've got the zero vector. See that? So these are linearly dependent because there's a way to get the zero vector without all of these things being zero. On the other hand, go back to this one again. Remember I said this one was linearly independent. There's no way I can get this from the other two. Because look, there's just no way. There's no way I can get a 0 here unless I get a 0 in front of this matrix right there. And then I'm also going to need a 0 in front of this one. And I'm also going to need a 0 in front of that one. Okay? So the only way that I can get those three things to add to the zero vector is if all these three things are 0. Okay? So that's what it means to be linearly independent, is that the only way they add up to the zero vector is if they're not. If they're linearly dependent, then there's some other way to do it. There's a way to do it like, let's go back to this. Well, okay, I've already done it, okay? So to be linearly dependent means basically I can write one in terms of the others, okay? So this is kind of a review. I'm not trying to give a full explanation of this. This would take much longer lectures and everything else. But that's the idea. Okay? Now, once you have that idea, now let's go back to this again and ask this question. How many vectors does it take to span this space? Do you agree that I can get all the vectors in 2 by 3 matrices by starting off with these vectors right here. Do you agree that I can get any vector I want in here by starting off with these and by taking a linear combination of these vectors? In particular, if I take A times this one and B times this one plus C times this one plus D times this, E times this, and F by this, add all those together, I'm going to get that particular matrix. So no matter what matrix you give me in 2 by 3 matrices, I'll be able to get them by adding these together. So this set right here, it's linearly independent, and it also spans all the 2 by 3 matrices. So it's the most efficient way if you want to span, if you want to generate all of these matrices, this collection will do it. You've got everything you need, but you don't have anything extra. I could throw another one in here. I could throw 2, 5, 0, 1, 3, 1. I could throw this in there as well. It's certainly the case that this collection of 7 vectors right here, this spans R3. In particular, I might not even need this one, or I could use it and make lesser use of some of these maybe, depending on what my vector is up here. So I could throw it in there, and the span is still going to be the same. I'm not going to get anything more by adding this one than I did just by getting these. By getting these, I'm getting the whole space. This doesn't hurt anything. It doesn't increase the span at all. It certainly doesn't decrease the span. It's just extraneous. It's extraneous. So this collection is no longer linearly independent because I can get this one here by taking a linear combination of these. I can get this one. Okay? So this is a collection right here, which is the most efficient way to generate all of these matrices. And so any collection which is both linearly independent, which means you don't have extra things, plus it does the job. If I didn't have this one here, let's get rid of this one. If I didn't have this one here, now that's a linearly independent set, but I can't get everything. I can't get anything with a 5 down here, because I need something. I need something with something right here in the bottom corner in order to get it. So I won't be able to get all the matrices, all the 2 by 3 matrices that way. So I both need to get the job done, but I want to do it as efficiently as possible. And something which is both linearly independent and also spans the space, that's the most efficient way to do it, okay? And so something that has those two characteristics is called a basis, okay? If you have more, you can have more than one basis, that's plural, bases, okay? But anything which is both linearly independent and also spans the space is called a basis, okay? And the number of things in the basis, 1, 2, 3, 4, 5, 6, that's called the dimension of the space. So the dimension of V is the number of things, number of vectors in a basis. Okay? And I'm skipping lots of theorems here. One of the theorems you have to show is that any two bases are going to have the same number of elements, and that's all true. But we're not going into all that material here, okay? So these are the key ideas, and now that we have them, let's apply them to some other vector spaces as well. Let's go back to the polynomials. Let's go back. Let's be very specific. Let's consider the 5th degree polynomials. Okay, I can't remember the notation, but the 5th degree polynomials are going to be things of the form a5 times x5 plus a4 times x to the fourth power plus a3 times x cubed plus a2 times x squared plus a1x plus a naught. Okay, it's all things like that. Let's let that be our vector space. Do you agree that that's a vector space? What do we have to show that it's a vector space? We have to show that basically all those 10 things have to be true. So sure, if I take two of these things and add them together, I'm going to get something else that looks like that. If I multiply them by a constant, I'm going to get something else that looks like that. If I take two and add them together in either order, let's just use p for the polynomial. One polynomial and then the other, it's going to be the same as if I add them in this order. Okay, and the zero polynomial is just the one which is just 0 times x5 plus all the way down plus 0. That's just your zero polynomial. What are the negative ones? If I have this one, then this, of course, will be something that if I add to it, I'll get this one. So it has all those properties. Okay, so that's a vector space. Okay, now that that's a vector space, let's find the span of these two vectors. The vectors x3 and x1. X. Okay. So what's the span of that going to be? That let's call that W. So W is going to be everything of the form a times x cubed plus bx. It's going to be everything of the form like that, where a and b are real numbers. Okay? So that's the span. It's all linear combinations of those things. Okay? So do you agree that that's a subspace? It's a subspace because if I take two of those things and add them together, I'm going to get something else like that. If I multiply it by a constant, I'm going to get something else like that. So sure enough, that's a subspace. And a basis for this then is x cubed and x. Okay, because do you agree if I take these two things are linearly independent, there's no way if I have ax cubed plus bx is equal to 0, the only way that thing can be equal to 0, this is for all x's of course, is if both a and b are 0. So it's linearly independent, and by taking all linear combinations of this, I get the space right here. Okay, I get this whole space. Okay, so it's a basis. It's not the only basis. Here would be another one. I mean, just to make one trivial, 2x, right? Because with these two things right here, if you give me anything you want, 5x cubed plus 8x, just give me something in W. Give me something in W, and sure enough, I can write 5x cubed plus 4 times this vector gives me that. Okay, so that's a basis. Okay, so there's lots of theorems and so on. I want you to just kind of get the main ideas from this thing. Let's just do a few more problems here. Let's let R2, all the vectors in R2, be the vector space. Okay, so it's just the normal vectors you have like this and so on. You could think of those as all being duples, where this is maybe the 3, 1, and this is a vector 2, 3 maybe, and so you have all those vectors. And so what are some various subspaces of R2? Okay, what are subspaces of R2? Is this whole collection of things here a subspace of R2? When I say everything that's in here, are all the vectors whose heads end up right there, all those vectors, is that collection of things a subspace of R2? And turn the video off and think about it, and then come on back and I'll give you the answer. Okay, for all these things, think about it first. You're ruining the whole thing if you don't think about it first. Okay, so here are the answers. That's not a subspace, because in particular, if I take this thing and multiply it by 5, I'm going to be out there. So it's not closed it's not closed under multiplication. See that? So it's not closed under multiplication. So that's no good. That's not a subspace. What about the collection of all things in here? That the head ends up in there. Is that a subspace? And the answer is no. The easiest way to see it is that it doesn't contain the 0 vector. The 0 vector is right there, and that's not in the set. So that's obviously not a subspace. What about all the things along this line right there? Is that a subspace? Well, that one is, because if you take any two vectors there and add them together, you're going to get something else there. Here's one, add it to that one, you're going to end up right there. So that's good. You multiply it by any constant, you'll be there. So that's good. So that is a subspace. Okay. What about all the things between these two lines? Okay, all the vectors that are in here. Are those is that whole collection of things a subspace? It first might seem like it is, because if I take this one and add it to this one, I'll end up right there. If I take these two, I'll end up right there. But notice if I take this one right here and add it to this one right here, add those head to tail, I'm going to be out here someplace. See that? So that's not a subspace. So that's not a subspace. Okay? So what about all the points along this line? Just all these vectors right there. That's not. It doesn't contain the 0 vector again. So right away you see that that's not, among other things. Okay? So it turns out the only subspaces of R2 are lines that go through the origin, or the whole thing, or the trivial one is just the 0 vector all by itself. Okay? Because you add the 0 vector to itself and you'll just get the 0 vector and so on. Okay? If you're in R3, what are the various subspaces? And it turns out the various subspaces there are any plane that goes through the origin, or just a line that goes through the origin. And again, the reason a plane that goes through the origin is because if you take any two vectors that lie on this plane, the heads lie on this plane, then if you add those two vectors together, you'll be another point on that plane. So that is a subspace, but those are really the only one. And then of course you can have lines that go through the origin as well. Okay? So yeah, let's go back to 2 by 3 matrices again. It's all things of the form A, B, C, D, E, F. Okay? Can you find a subspace of degree 3 for this? So of degree 3 means that you're going to need 3 linearly independent vectors to generate it. 3 linearly independent vectors whose span is that space. So I'll give you one right here. How about this space right here? I'll let W be everything of the form A, B, 0, 0, C, 0. There. Because I can see that it's going to take vectors like this, would be kind of the easiest ones. Those three vectors, they're linearly independent. There's no way I can get one from the others. Oops, I meant to have a 0 here. Okay? And this is a 1. There's no way I can get one from the other, so they're linearly independent. And if I take all linear combinations of these, I'm going to get this. I'm going to get W. See that? So this is a basis for this. And so this is linearly independent, and it's a basis. So the dimension of W is 3, and there's a basis for it. Here's another one. I could make this my subspace, and now here's a basis for that. Okay. So that's the idea. See if there's anything else. So the key is if the dimension of W, the dimension of W is 3. So there's several things I know. I know that I'm going to need at least 3 vectors in order to span it. Okay? I'm gonna need 3 vectors to span it. If I have more than 3, some of them are extraneous, but I'm gonna need at least 3 in order to span it. And I know that if I have anything more than 3, I know that it's going to be linearly dependent, because 3 gives me the whole space. The linear combinations of 3 of them give me everything. So if I have more than this, if I have anything in here, 1, 2, 0, 0, 5, 0, which, oops, I'm back to this one now. There's something that's in there. Okay? All I need is these 3. I don't need anything more than those 3 in order to generate this thing. Okay? So if you look at some of the problems in the book, it says any basis, well, I'll let you read it. So you read the exercises. I'll just mention this, that a really nice physical example that catches these ideas is this. If you're told by an expert backpacker that if you're going to go on a week-long camping trip, backpacking trip, that if you have a backpack that weighs, or let me say it this way, if you have a backpack that contains everything you need but nothing extra, it has everything you're going to need but nothing extra, that's going to weigh 50 pounds. Okay, that's what the expert backpacker tells you. He says once you've got your tent, your sleeping bag, your can opener, everything you need, it's going to weigh exactly 50 pounds. Okay? Then there's 2 things you know for sure. You know for sure that if your backpack only weighs 40 pounds, you know for sure that you don't have everything you need, right? You know for sure you have not packed everything you need. If you have a backpack that weighs 70 pounds, you know for sure that you've packed something extra. You've packed more than you need, okay? If you happen to have a backpack that weighs 50 pounds, well, you don't know for sure, right? It might be that you've got some things that are extra and that you also have some things that you don't need. Did I say that right? Oh, no, it might be that you have some extra things and that you also aren't including some things that you do in fact need. So there's no guarantee that just because it's 50 pounds that you've got exactly what you need there. So that it's like a basis, right? It's like a basis. If we know that the dimension is 3, just because you happen to have 3 vectors here, there's 3 vectors, that doesn't necessarily mean that it's linearly independent, and it doesn't necessarily mean that it's going to span that thing, right? So you could have something extra, and you might be forgetting something that you need. But what you do know is that if the dimension is 3, just like 50 pounds, you're told by the expert that you're going to need 3 linearly independent vectors. So everything is needed, and you've got everything that you need. Okay? There you go. So this lecture is meant to kind of augment the book, and now you've got a bunch of exercises to follow and make sure that you understand the ideas. Okay, very good. Hi everyone. It occurred to me that it might be helpful to give some help with the exercises in section 5.2. So let's look at some of them. I'm going to do something very similar to exercise 5.2.12. First of all, where I say consider the following vector spaces, and then I ask several questions. So let's take one that's not on there, but it's similar to one that is. Let's take the set of all polynomials, or I should say the space of all, let's say, third-degree polynomials. Okay, so the space of all third-degree polynomials, I'll use the same notation I have in the book, is everything of the form, I'll call it a3x3 plus a2x2 plus a1x plus a naught. Okay, so anything of that form is a third-degree polynomial. So for example, 7x cubed plus 2x squared minus 15x plus pi squared. Okay, that would be a constant, of course. That would be 1. One of these constants could be 0, so that would be 1. Okay, this constant could be 0, so that would be 1. Anything that is of this form, where these are any real numbers you want, that's something in P3. So in pre-calculus, you just learn this to be all polynomials that have powers of x up to and including 3, but not greater than 3. Okay, so there's our vector space. Why is that a vector space, first of all? Let's think about it. If I add two things like that together, I'm going to get something else like that, right? If I have x cubed plus x, and I have 3x cubed plus 2x squared plus 8, x plus 9, then I add those together and I'm going to get 4x cubed plus 2x squared plus 9x plus 9, right? So you can add them together. If you multiply them by a constant, you're going to get something which is in P3. What else can you do? It doesn't matter which order I add them. I can add them in any order, and either order, and it's going to be the same. It satisfies the associative property. There's a 0 element. What's the identity element? The identity element is just going to be the 0 polynomial. 0x third plus 0x squared plus 0x plus 0, which is just 0, right? If you add that to any polynomial, you get that polynomial back. What's the inverse of 3x cubed plus 5x squared minus 9x plus 5? Do you agree? It's going to be negative 3x squared minus 5x squared plus 9x minus 5. You add those together and you get the 0 one. So you go through all those 10 properties, and yeah, they all are satisfied. So this is a vector space. Okay, that's a vector space. So that's the first thing you should note. So once we have that that's a vector space, here's the question I ask. Choose a set of vectors and determine the span of S. So I'll just choose a couple easy ones here. Okay, I'm just going to let my set be equal to x and x squared. There's my set of vectors. Okay, there's my set of vectors. What's the span of that set? So if I take all linear combinations of this set, what am I going to get? So if I take any alpha times x plus beta times x squared, that's going to be the span. This is my set, so this is the span of S. Is going to be everything of that form where alpha and beta are just any real numbers. Okay, so what would those things look like? 5x plus 9x squared. Whatever. Agreed? So there's one. Let's try another one. Suppose these were my two vectors. Okay? What would be the span of that? So I take all linear combinations of that, and what's it going to look like? It's going to be something of the form alpha times x squared plus beta times x plus 2. Okay, so it's going to look like this. Alpha x squared plus beta x plus 2 beta. Okay, so what do those polynomials look like? Notice that they're not going to have any x cubes there. They're going to have whatever you want for x squared. You can have whatever you want. You can also have whatever you want for x's, but notice that whatever you have for x's, you're going to have twice that for the constant. So if you happen to have a 3 right here, then this is going to have to be a 6. Okay? So it'd be things like that, for example. Okay? So there you go. Okay? So that's choose a set. Okay. Choose a set of vectors that is linearly dependent. Okay, what would be a set of vectors which is linearly dependent? Well, what about x squared and 5x squared? Y'all agree that that's linearly dependent because I can get this one as a multiple of this one. So that's linearly dependent. What would be another set? I could choose x squared, x, and then 3x squared plus 7x. Do you agree that that's a linearly dependent set? Because I can get this one from a multiple of these. If I take 3 times this one and add it to 7 times this one, I'm going to get this one. So that would be a linearly dependent set. Agreed? So those would be linearly dependent sets, for example. Okay? Choose a set which is linearly independent. Well, how about x cubed and x plus 5? How about just those? And let's take 7. Take those 3. Okay? There's no way I can get this one from a multiple of these two. There's no way I can get this one from a multiple of these. No way I can get this from a multiple of those. Okay? They're linearly independent. Okay? I could have just let this be x2 and gotten something that maybe looked a little easier. Again, there's no way to get one from the others. Okay? So that's a linearly independent set. Okay? It's linearly independent. Okay? Find a basis for the vector space. Well, for a basis for the vector space, we need a linearly independent set, and we need one whose span gives you everything. So the easiest would be, I'll choose beta for my basis. Maybe the most typical looking one would be just this. There's the basis. Because do you agree that there's no way I can get any of these from a linear combination of the others? So they're all linearly independent. And also, the span of this gives me everything, right? If I take linear combinations of this thing, linear combinations are going to be some constant times this, plus a constant times that, plus a constant times that, constant times that. I'm going to get everything. So this is a linearly independent set, which is also spans the entire space, and so this would be a basis. How many elements are in this basis? 1, 2, 3, 4. So now we know that the dimension of this space is 4, and any basis is going to have exactly 4 elements. Okay, we could choose a different. Let's just make it trivially different. Put a 2 there. Okay, there's a different basis. Okay, it's different from the first one, but they're all still linearly independent, and the span gives you everything. Okay, so there's that. Let's see, find a basis. Okay, so that's the kind of thing I want you to do. Okay, on those problems in exercise 5.2.12. Okay, let's go on to 5 to 14, and let's just get started on some of those. Here's what you're told. You're told that you have a vector space, and the dimension of the vector space is n. Okay, it's n. N is some fixed number. Okay, let's just choose it to be 5, just to be very concrete. Say the dimension of v is equal to 5. So there are five elements. So I know that every basis for v is going to will have exactly 5 elements. Okay, and it's kind of like saying that a backpack that has everything you need and nothing extra will be, say, 5 pounds. Okay, so it'd be like a backpack that has everything you need and nothing extra. That's what a basis does. They span the entire set, but there's nothing extra. So they're linearly independent. You need every single one of them in order to get the space. So it's like saying a backpack is going to be exactly 5 pounds. Okay, and so then let's answer some of these other questions. Well, I basically answered the first one. Any basis will have exactly 5 elements then. Okay, every basis will have exactly 5 elements. That's number 1. A set with fewer than 5 elements must be, may be, or cannot be linearly independent. Okay, so think about your backpack. If you know that you need 5 pounds in order to have everything that you need for your trip, and you have a backpack with 3 pounds, is it the case that everything in that backpack is going to be needed? Okay, is it true that everything in that backpack is going to be needed? Or I don't know. We can either think of it that way, or let's think of our polynomials again. Let's take P4, which would have this as your basis. There's a basis for P4. There's a 4th degree as well. Okay, so there's a basis for P4. Notice it has 5 different elements in it. Okay, so there's a basis. Okay, so the question is, if you have a set with less than 5, what do you know about it? Well, here's one set in P4 that has less than 5. Okay, that has less than 5. Notice that one's linearly independent, right? It's linearly independent. None of these can be gotten from the others. Here's another set which has less than 5. I'll just do it like this. There's another set of vectors. There's a set of 3 vectors. Notice that this set of vectors is linearly dependent, right? So if you have less than 5, if your dimension is 5 and I have something less than 5, maybe it's linearly independent, maybe it's linearly dependent, just like a backpack. If you have less than 5 pounds in your backpack, maybe everything is needed, maybe everything's not needed. Maybe you have two shovels in your backpack, okay? So either one is possible. So the answer would be, it may be linearly independent. You don't know. A set with fewer than n elements must, may, or cannot span V. Okay? So here's your, here you need 5 in your basis. If you have 3, if you have less than 5, is there any way that this thing can span all of P4? In order to span all of P4, you need every polynomial that has those elements in it, okay? It's got to be something of the form. It's got to be everything of the form. It's got to be able to give you everything of that form. So can I get everything of that form if I only have these 3 vectors? No way, right? I won't be able to get anything with a constant in it. I won't be able to get anything with an x to the 4th power in it. So if I have less than 5 elements here, there's no way that I can span the entire set. There's no way, okay? It's impossible. Okay, so that answers number 3. Okay, let's do one more. A set with more than n elements, what about being linearly independent? What if I have more than in this case, 5 elements, okay? Well, let's think about it. So I have more than 5 elements. So let's take these to begin with. There's 5 right there. Those are linearly independent. As soon as I throw in any other polynomial in P4, it's got to be something else. This is my world right here. If I throw in anything else in P4, like what? X to the 4th plus 7x squared. There's another one. What do I know? I know that this basis right here already generates the whole space. Linear combinations of this give me everything in the space. So as soon as I throw anything else in there, I know that I can get this from a combination of those. So this thing right here has to be linearly dependent. If I have more than 5, for sure it's linearly dependent. Okay? So that's the idea. Okay? So I'll let you go on with those. But that's the kind of thinking there. That you need. Okay? I'll let you keep working on that. If you can answer all those questions and they all make sense to you, you really understand these notions of linear independence and span. Okay, then let's also work together on this one. It occurred to me that this is a really important problem for you to do, but I might as well help you with it. Okay, so you can do it. You'll be responsible for it, but let's do it together. So here's what we're told. We're told that x and y are linearly independent and I want you to show that these two vectors are linearly independent. Okay? If these two are linearly independent, show that these two vectors are linearly independent. Okay? So let's do it. So here's the process. Proof. This is a nice mathematical proof here. We don't do too many in this class. We more solve problems, but this is a nice example of a... Okay, my computer just stopped on me. Okay, so we to show that two things are linearly independent, we say a constant times one plus a constant times the other is 0, and in order to be linearly independent means that the only way that can add up to the 0 vector is if these two constants are 0. So we must show that alpha and beta have to be 0. Okay, so that's what we have to show. Let's see if we can show it. So what do you do with that? There's really not much you can do. Heck, about the only thing I can think of doing is maybe using the property of vectors that you can multiply it out. So I know that alpha x plus alpha y plus beta x minus beta y has got to be 0. So that's got to be true. Well, now maybe I can reorganize things. I have beta times these two things, so I can write this as alpha plus beta times x, and then alpha minus beta times y is equal to 0. Notice that we're making use of all the properties of vector spaces here, right? That this is the way you distribute constants, and this is the way you distribute constants, and so on. So, or vectors. So we're making use of all these properties 1 through 10. Okay, so now, what are we assuming? We started off with this is 0. That implies, so we know that that's 0. So given that that's 0, that implies that this is 0, and that implies that this is 0. Now, look at what we're doing. We are assuming that x and y are linearly independent. So since x and y are linearly independent, that is, they form a linearly independent set, I know that what's got to be true. If they're linearly independent, then if you multiply one by a constant and multiply by another constant, and that's equal to 0, these two constants have to be 0. So since those two things are linearly independent, I know that these two constants, alpha plus beta, has got to be 0, and alpha minus beta has got to be 0. So I know that those two constants have to be 0. But now I can make use of just what I know from algebra. If these two are 0, I can add these together and get 2 alpha is equal to 0, and that implies that alpha is 0. And once I have that alpha is 0, that implies that beta is 0. So boom, I did it. I just showed that both alpha and beta have to be 0, and that's what we had to show. So there you go, right there. We just proved that that if x and y are linearly independent, then these two vectors are linearly independent. And like everything else in this course, everything that we learn is going to be used, okay? There's nothing that I'm giving you as an exercise that's kind of nice, but you don't really need it. Everything is going to be important as we go on. So there it is right there. This is 6-2-15, and you can do 6-2-16, which is kind of similar. Okay, very good. So there's some extra help in section 5.2.